Discover the latest advancements in network security at Intersect 2024, a virtual event from Palo Alto Networks where industry tech and cybersecurity professionals discuss how advancements in SASE are reshaping expectations. Topics include a secure enterprise browser, using SASE to secure and accelerate applications, and more. Intersect 2024 is available on demand now at intersect.paloaltonetworks.com. Welcome to Heavy Networking, the flagship podcast in the Packet Pushers podcast fleet. I'm Drew Conry Murray alongside Ethan Banks. Today we're talking about using Ethernet as the network fabric for AI workloads such as model training. One issue is that AI jobs don't tolerate latency, packet or frame drops, and retransmits. So in other words, AI workloads do best with a lossless network. And while Ethernet has proven to be a robust and useful protocol over the decades, it was really never designed to be lossless. However, major efforts are underway by ASIC makers, switch vendors, and industry groups to optimize Ethernet to make it a suitable network fabric for AI jobs. So on today's episode, we're going to talk about those efforts. We'll explore different optimization techniques and discuss general design considerations to be aware of if your organization decides to go down the Ethernet path for AI. Our guests are Chris Kane, Senior Manager of Systems Engineering at Arista Networks, and Pete Lumbus, Principal Engineer at NVIDIA. Chris and Pete, welcome back to Heavy Networking, and let's dive right in. What makes jobs like AI model training different from workloads that Ethernet typically supports in a data center network?
Yeah, absolutely. So glad we're having this conversation. It's a popular topic, around the industry.
Yes,
for sure. Yeah, there's definitely an element of, we can't leverage just-in-time research for these designs and these builds because the workloads are different, right? Regular data center workloads often act independently, whereas in these AI solutions, these AI workloads, the GPUs are going to work together. They're going to work as a collective, and they're distributed in that workload demand calls upon resources throughout the entire data center, whether it's GPU to GPU, the CPUs involved, and storage. So I think it really takes us back, a couple of decades ago. It might have been Sun Microsystems that said, the network is the computer. And I think we're really living that right now. So for the training and inference workloads, there's significant demand placed on the network. When you're talking about jobs that are run not only for minutes, hours, days, but they could be weeks, or in some cases, you've heard about these large LLMs that'll run for months on end as they do their training. So depending on the type of job, we'll see a variation in load, and we'll see a variation in spikes. So there'll be bursts of traffic. Some will run in sprints, and then some run more as that marathon load on the network, where we'll see interface utilization at nearly 100% for about 100% of the time. So we'll see a constant, it's not uncommon to see a constant 360 to 370 gigabits of traffic on a 400 gig interface.
Now, one of the things you mentioned, Chris, along the way, you're talking about GPUs and so on, working in a distributed fashion for the problem that they're trying to solve, and that I think is a key point here. The GPUs are working on a problem. They're not, if it's a cluster of just 10 GPUs to pick a simple number, they're not working on 10 different little problems exactly. They're working on one problem that's been distributed across them, meaning if a chunk of data doesn't get to one of the GPUs, the other 9 in my imaginary 10 GPU cluster would all be idled. Is that right?
Oh, yeah. And heaven forbid an idle GPU, right? I mean, if anybody has quoted these things out, GPUs or accelerators, whatever you want to call them, depending on the manufacturer, they're quite expensive, right? So idle GPU time is certainly something that a network engineer would get yelled at if the platform owner thought we're responsible for an idle GPU. But you're exactly right. So we'll take this big chunk, this big workload, and it's going to be divvied up across all the GPUs. Now, there's different collectives. There's different ways they'll communicate with each other. If you're new to this space, you might hear things like all reduce or all gather. So we'll see, that'll be some of the variation that we'll see in the network. It's not always a consistent load. And I think that's what makes some of the design and really some of the operation challenging. But because they're so dependent on each other, the GPUs are working in a synchronized manner, right? And so in order to complete their own task, a lot of times they have to wait on another GPU to complete its tasks. And therefore, it's been my experience for the proof of concept tests or the production deployments I've been involved with, There's a couple metrics that folks want to look at very closely. So if we can introduce about 1,000 new terms to the audience during this podcast, right? JCT, right? Job completion time. And another one is TSN, or time spent in networking. Those are two things they're usually looking for, keeping a close eye on, and then, pivoting to whether the network is contributing to a delayed or slowed down job completion time. Hey, we ran the exact same job on the exact same data yesterday. It took an hour. We're rerunning it today and it's taken 3 hours. What's going on? And in the time spent in networking, we are moving data around, and we do need to leverage, a collective of GPUs to chew through this. And therefore, we have to send this data out onto the network for a lot of these tasks. So I think the industry numbers right now are somewhere around 20 to 50% of the time of a job can be spent just getting data across the network, right? So it's not that it's only residing inside of a host or a system, but that data and the results as the GPUs communicate with one another, or perhaps go to grab some more data from storage, can be a considerable amount of time. And that's what we're watching for as we optimize, and we'll get into this later, but our QoS settings, our load balancing settings, the visibility that we have, whether we're writing out to the network or the GPUs are communicating to each other inside of a host system. Because that's another element here that I think will be new to a lot of network engineers is, hey, there might be a time where it looks like the network, but it's actually not. It's inside the host. There's networking inside the host that you don't own. And so visibility into that will matter too. So yeah, the job completion time and the time spent in networking are certainly what we're aiming to drive down. And that's where you get into the problem of delays or packet loss that can affect any single flow that then infects the entire job that we're trying to get completed.
What was the percentages again of the time spent in networking? I
think what I've seen from Meta and Alibaba, some of the other ones that are very transparent about the projects they've had going on for a few years now, I believe the numbers I've seen are 20% to 50% of the job's time can actually be spent really waiting on data to fly around the network.
And that can be twofold. One is pulling that data in, right? You're pulling in, say, 700 terabytes because you've downloaded the entire internet and you're going to train on that. Yeah. So one is just pulling data into the nodes. The other part is, kind of talked about like the all reduce, 10 or 15 years ago when Hadoop was a big thing, it was all about map reduce. It's basically that same concept. So I'm going to take a job. Let's say I'm going to add all the numbers between 1 and 100. Well, I'm going to give every set of 10 to a GPU. So one GPU will add up 10, 11, 12, 13. The next GPU will add up 21, 22, 23, 24. So that's the distribution of the work to each GPU. And then once you finish counting your numbers, once you've done your little bit of job, everybody has to come back together with their answer to be able to do the next part of the job. And so you end up sending either those huge flows like that, and that's where, talking about the internet, the network being at zero because we're churning on GPU or we're transferring data, and then goes to 100 for that data transfer. And then the other part is being like, okay, I have an answer. Let me send it to everybody. And getting that data transfer there. And so again, back to loss and latency, if there's delay in getting that data, that GPU is waiting. If there's loss and you have to retransmit, you're waiting for that timeout, you're waiting for the retransmission. And that whole time, nobody can do anything because I need all the answers before I can move on to the next question.
One more point then, following up on what you were describing, Chris, about long running. You said some of these jobs can take months?
Yeah, absolutely. And again, going back to some of the transparency and information sharing you get from like Meta, I would definitely, if there's a resource list we want to put out there, I would put Meta at Scale. Is one of the great resources where a couple times a year, maybe quarterly, they'll be very transparent about their projects, their jobs, what has worked, what hasn't worked, the amendments that they've had to make. And yes, they'll describe some of these can run for weeks and months at a time. So then you get into areas of things like checkpointing. If I could have a problem, I have to dial back to a point. How often do I checkpoint? Because presumably if I'm checkpointing, I'm not processing the data, right? I'm not working on a job. I'm busy doing something else. So yeah, it can be surprisingly long periods of time for high levels of utilization that we may see on the network as these jobs work to completion.
To come back to that previous example, I was talking about counting numbers 1 to 100. What if I want to count to 1,000,000? I break it up by tens again. So I get every, set of tens. I combine all those together and do the next set, 210, 220, 230. And then the checkpointing is, well, when do I save that where I'm at to disk? Do I save it after every one of those? And so I have lots of little delays. Do I save it after every, say, 1,000 numbers that I've added together, after every 10,000 numbers? And what happens if there's a job failure, like a network outage, everything before that checkpoint is gone. We basically start over and we don't trust the data anymore. And so the longer I go between checkpoints, kind of the faster I can keep that momentum going. But when something eventually dies, whether it's a GPU, a disk, a CPU, the network, I lose that data and I start back over. Again, to Chris's thing, Meta actually produced a paper at SIGCOMM or something last week that was phenomenal, talking about their use of large scale Rocky networks. And we'll talk about Rocky in a second. But it really talks a lot about like what failure modes were they seeing? What are some of their challenges? How did they build it out?
So this challenge sounds similar to what, remembering back in college writing term papers, like how many pages do I write before I have to put a disk in and hit save? I'm trying to balance out getting this paper done and then stopping to save it. And
you're aiding yourself by saying both disk and save.
I know. Yeah. Definitely aging myself.
All right. A save point in a game?
Yeah. I should have said that.
Talk about those failures. Not everybody's going to build these, crazy public infrastructures that, we hear about 150 megawatt data centers, 200 megawatt data centers, 100,000 GPUs in a cluster. But though there are a lot of components here. So even if you only had a 10,000 GPU cluster, another good resource to leverage is SemiAnalysis, who regularly puts out detailed reports of what's going on in the industry from a semiconductor level. And they did an analysis, if you had 10,000 GPUs in a cluster and you had optics with a 5-year MTBF, you'll have your first optic failure within 4 hours of lighting up that infrastructure. Because there are that many components involved, right? And we'll get into why there's additional components, the over-provisioning, the amount of bandwidth we have to have between leafs and spines. There's other elements here to kind of explain why there's so many components. But just, thinking about the MTBF shows up probably a lot faster than people would have anticipated.
Okay, so I think you guys have made a good case for why loss and latency can be detrimental to AI workloads. So the next question is, there is a lossless network protocol, InfiniBand. It's already available. So how does InfiniBand very briefly compare with Ethernet as a network fabric for jobs like AI model training, inference training, and so on?
Yeah, so InfiniBand, it is an open standard. It's the InfiniBand Trade Association or something like that. But, most of the InfiniBand in the world comes from NVIDIA through their acquisition of Mellanox. Yep. The big thing that InfiniBand provides is it's much more plug and play than Ethernet. There's a software controller called like a fabric manager or something like that. And it's basically provisioning the network and doing all the routing and switching and everything that you would think of. It's a totally different layer 2 and above format. So it's not Ethernet, it's InfiniBand. It's totally different. But what it does is, at the simplest, is it does end-to-end credits to make sure that whatever it is that you want to send, there is guaranteed bandwidth and buffers from one port to the next, from one NIC to the other side. So you actually extend your applications to say, hey, when you request a chunk of memory on a remote machine, you're going to say, I need whatever, I need 64 bytes of memory to make this request. You will make that request to the operating system. The NIC driver, the InfiniBand NIC driver, will hear that, and it will go out and it will request 64 bytes of bandwidth end to end, and actually ask from one link to the next, hey, do you have this space? The switch will make sure it allocates the buffer to make that transfer. And if there isn't, you will just wait. And so it feels like latency. It's like the difference between downloading a file locally and downloading one from the other side of the planet. It just feels like latency. But then you guarantee to never have loss in that regard. And then the other thing that InfiniBand provides is what's called in-networking compute, or SHARP. I cannot remember what SHARP stands for, but in these all reduce, like I said, everybody sends out their problems, they compute an answer, and they start to send back the results. The switches can actually understand those results in certain cases and, combine them on the switch. So that way the switch is adding, say, the 48 ports of results instead of sending 48 times however many racks or the results out. So it can do some of that addition and combination for you, or it can figure out do deduplication and make it look a little bit more like multicast and traditional Ethernet.
So Sharp, I did a quick look, Pete. Scalable, hierarchical, aggregation, and reduction protocol. Does that help?
Yeah, they Ivy likes their terms.
Okay. So InfiniBand does all of this. It reminds me of Fiber Channel SANs with credits and reserving things. Reminds me a little bit of RSVP,
Absolutely.
where you get an end-to-end reservation of bandwidth and so on, and again end-to-end. So what are we messing around with Ethernet for then? InfiniBand sounds like the thing. It sounds like a good solution. So what are we doing with Ethernet, which is not designed to do any of this stuff?
It's what's the old saying, like good, fast, cheap, pick two.
Right.
And Ethernet is like always been throughout its whole history of that sweet spot of being the right two, whatever those two needed to be. And so historically, InfiniBand has had a little bit of a speed edge that has more or less gone away in like the 400 gig era. So one, Ethernet's caught up. Two, now that AI is so big and so pervasive, you're seeing a lot of people looking at these AI workloads, which look exactly like supercomputer workloads of old. And all the supercomputers, most of them, are built on top of IB, InfiniBand. Mm-hmm. Now the market's bigger. Now folks are trying to solve this problem with the things off the shelf, right? I don't want to build and manage an InfiniBand network that sits next to the Ethernet network that I built and manage. Like I want to use the same tools and the same vendors and the same protocols and technologies. And so that's really the push there. But again, like you said, Ethernet isn't lossless. And so, you now have to be like, well, what do we do about that? How do we fix it? And that's where technologies like Rocky come in, or RDMA over converged Ethernet, which is what exists today, and whatever the Ultra Ethernet Consortium is doing, which I still don't know.
Yeah, I think you're going to have to take back your snide remark about IB liking terms, because Ethernet for AI also likes its terms, which we will get into. But I also want to run this idea by you. It also seems like, essentially the companies who sell Ethernet gear have also seen the rise of AI and thought, hey, maybe we can get some of that IB money. Is it also fair to say that they have a vested interest in making this happen?
Absolutely. I mean, they have a vested interest in making it happen. And I also think that if you look at the broader industry, I'm not an analyst, but there's not like a ton of Ethernet growth per se. I don't want to say we're stagnant, but most of the networks that exist are fast enough today. The hyperscalers are doing their own thing, so it's harder to sell into them. A lot of folks don't need more, right? Compute's getting bigger and bigger, so I can just shove more and more VMs and containers in a couple of nodes. And so now all of a sudden you have this like greenfield growth opportunity to sell a ton of ports of your most luxurious, gold-plated Ethernet.
Yeah.
Everybody wants in on that.
Yeah. My assumption is the customers for the 400, the 800, and the 1.6 TB are going to be AI and not your typical enterprise data center.
Absolutely.
Yeah, they're early adopters for sure. And I think another part might just be the familiarity, right? Not only with tools that understand Ethernet, but engineers that understand Ethernet versus IB. And then for others, it could be that multi-vendor approach, right? I'd just rather not be beholden to one source, right? And there's some diversity there that might play in. It's one of those things where it doesn't always have to be a technical reason, right? It could be geopolitical, it could be a business reason. But so there could be several factors that go in deciding whether you want to go down the InfiniBand route or the Ethernet route, which probably leads at this point to talking a little bit about, there's a couple of networks involved here when we do these builds. There is a concept of what we call the front end network. And then there's the idea of a back end network, right? So and you can see a mix of use where the front end network may be Ethernet and the back end network may be InfiniBand, right? Or maybe both. Maybe it's Ethernet all the way through.
But there's a front end network, Chris, or maybe multiple front end networks, if you will, because you're plumbed up to a management interface and you're plumbed up to a storage network to retrieve data. And then the processing is the back end network that's InfiniBand or your 400 or maybe even 800 gig Ethernet, something like that.
Yeah, spot on. And it's, the front end network I like to think of or describe as the CPU network, or what we've kind of worked with for a lot of us our whole careers, where I'm networking for CPU connectivity. And that's usually where we see the storage connected in as well as on the front end network. And then on the back end network, we talked about the sensitivity, whether it's loss, latency. The last thing you want to do is throw other flows in between those GPUs, right? So I'd rather have dedicated switching or dedicated networking gear providing the path for the GPU to GPU in that backend network. So that's it's a dedicated part of the infrastructure that we're looking at, providing the pathways for its GPUs to talk to one another. So even as you see public statements, from some of these large projects, and they talk about who's involved, when you really dig into the weeds of what's going on there could be huge differences between where the IB is deployed as to where the Ethernet's leveraged.
Let's pause for a word from sponsor Palo Alto Networks. You can discover the latest advancements in network security at Intersect 2024, a virtual event where industry tech and cybersecurity professionals discuss how advancements in SASE are reshaping expectations. Topics include the next chapter of SASE, securing workspaces on managed and unmanaged devices with a SASE native enterprise browser, mastering data security with AI, using SASE to accelerate application performance, and more. Intersect 2024 is available on demand now at intersect.paloaltonetworks.com. That's intersect.paloaltonetworks.com. And now back to the podcast.
We just pause for a second and think about the money tied up in this. It's astonishing. For just for the back end network, right? It's your, how would you describe it, Pete? The gold plated, the very best Ethernet you can buy these days. If you're going with Ethernet, InfiniBand, it's probably going to be even spendier. And that's just the one network. And then there's the machine itself that's got GPUs on board and all this stuff. That wasn't a cheap thing to stuff in a rack at times, however many thousand to build out the model you're trying to build out. And what's the ROI calculation on this? Because someo's got to have done it and think they get money back.
The ROI is infinite. There is no 1 billion.
I don't know, man. It's just, I know it's.
What's wild to me, seeing what the CSPs are doing, the Microsofts and Googles, like they literally can't get enough, right? Like they're taking stuff that they bought a year ago and putting it in the trash to replace it with the new stuff.
Wow.
Like they're like, yeah. And part of this comes back to the fact that, those jobs take a month to train, which means that we can't change any parameters and test again because it takes a month. But if the new GPU takes a week, well, guess what? That's a 4x speed up. That actually makes a huge difference for some of these really, really big things. And I think that I'm not enough of a data scientist to know, what was the tipping point, but like there was a point where not only did they figure out the algorithms to do it with the neural nets, but there was enough GPU memory to actually start to load enough data in GPU to work on. And that's why there's this Cambrian explosion of stuff, is that we finally got GPUs with enough memory to make the workload interesting. And now all NVIDIA is doing, and I'm sure AMD is doing the same thing, is just being like, how do we just make a bigger set of GPU memory? And again, this is, part of the pause, like the systems that I'm working on, it's like, how do we make 72 GPUs look like they all have the same memory? We can't get any more memory on one box. So we're not just going to do like sockets and message passing. We're going to be like, no, it's all 72 GPUs of coherent memory. And I'm like, this is insane. I don't understand this. But
this is all,
demand.
These are still all bigger and better shovels, though. There's all this money going into the tooling to make a large language model, let's say, that does what and is making who money, so that the investment in the back end data center and the power and the cooling, much of which probably wasn't sustainable, has got to be worth something. Mm-hmm. How? So I'm sorry, this is all an aside. It's just one of those things that's been boggling my mind lately.
I have some of these same, like I said, I'm very close to it. And there are moments where I'm like, what the actual my maybe rose-colored glasses view is the people working on this, meaning the people actually like building the AI things, like GPT and whatever the image thingy generator is, like that's cool and everybody understands that. But I think that there's like a whole level of research and work that's like, they're like, yeah, we're going to, once we crack this nut, like we now get to take all the money. That's my assumption. I mean,
yeah, they backed away from it. They were talking AGI for quite a while. And that's everyone's kind of like, well, we're not going to get there with LLM. That's not what LLMs are.
Yeah.
And so let's step back with a few challengers going, no, well, we don't even know how thinking works. Maybe we're all LLMs. And anyway. Well, guys, let's get back to the conversation now that our minds have all been blown here for a minute. The main challenges of using non-optimized Ethernet. If I'm just using standard Ethernet, it's really fast, but it's not lossless and so on. What are the big problems I'm going to have using for these kind of workloads?
Yeah, I mean, if you're experiencing loss in Ethernet, if you're experiencing loss in your AI training, again, it comes back to that checkpointing, right? You're just going to start over, and so there's the only way to really get around it is to make sure it's lossless. And, loss is really bad. Latency can be bad. The challenge with latency is that you end up idling those GPUs, like Chris was talking about, right? And so you want to eliminate.
Completion time goes up.
Exactly. And when we think about latency as network engineers, we generally think of it like kind of small, like, oh man, I have to download this like 10 gig file. This might take minutes. And so like if we're adding some latency along that path over a couple of minutes, like who cares? If I'm adding that same latency to a job that's running for 74 days, all of a sudden that's like hours and hours worth of latency that was thrown in the mix. And I think that's one thing that has broken my brain a little bit as I've thought about this, is that things that I've traditionally thought as like BS who care problems, it's because our transaction time is maybe measured in minutes in the network, in the Ethernet, traditional networking space of Ethernet. In the AI networking space, it can be measured in weeks or months. And now all of a sudden, every one of those problems, those little nits, compounds to be really, really big problems. And that's
we have to be talking about latency. The in between tiers of a leaf spine, I'm assuming, is the typical configuration that is measured in nanoseconds, probably, right? Is it that low?
That's part of it, but it's also just buffering, right? I mean, like there's think of buffer bloat on steroids kind of problem, right? So if I can eliminate all of my loss by just throwing bigger and bigger buffers at it, but if I now have things sitting in buffers forever, it's just as bad, and I've lost control, because now I'm going to say, oh yeah, you can transfer whenever you want, but now I don't have any control as a network administrator to, control the buffer depth or, use that as part of my toolbox.
But these problems coming up to me is what makes this space so exciting right now, because, these aren't solutions looking for problems to solve. You actually have problems to solve. And that friction, that grind leads to innovation, right? And to me, it's one of the most exciting times we've had in networking, where I can't take, for the gun nuts out there, I can't take a 22 caliber weapon and use it in a 357 Magnum world, right? Which is what we're talking about here, where I really have to strengthen and enhance some of the things that we've used forever, whether that's what we see with the Ultra Ethernet Consortium, trying to help out with Ethernet, where we talk about entropy to aid in load balancing, like how we have these minimal number of queue pairs and these long-lived flows. How in the world am I going to be able to move from a flow-based load balancing solution that we've been living with for a while now to go all the way back to per packet, or bit spraying, as some people may describe it. Or you get into changes in optics, right? Saying, hey, I want to get rid of the forward error correction because that adds like 100 nanoseconds of latency per transceiver. So, man, if I could get the FEC out of the way, then again, I'm driving down my job completion time. So whether that's, LPOs or even the co-packaged optics, like the Broadcom likes to talk about. So to me, it's the enhancements that ultimately will lead to even the average network engineer that isn't building 10,000 GPU clusters. I think we're going to see all kinds of enhancements to Ethernet and to the silicon that we're using in the switches. They're going to benefit us in other use cases as well.
Yeah, and we've seen that. Just looking at RDMA and Rocky V2, where that same InfiniBand topic or concept that I talked about earlier, where you make a request in your application for remote memory, and then the NIC intercepts that. We can do that over Ethernet, kind of using per queue pause frames. And so you think about a traditional QoS model where, I have my high priority, my medium priority, my low priority. We say, I'm going to put the AI traffic in the high priority, or, whatever subset of it. And then if there's congestion in that queue, we can actually have one NIC send to the switch can send to another switch and signal back pressure and say, hey, I'm getting full, you need to slow down. For the real old timers, I'm not going to name any names of anybody. We'll call him E Banks for anonymity. Maybe that's too out. Ethan B. But it's a lot like the frame relay Feckens and Beckons, right? That ability to signal back and say like, hey, I'm under congestion. You need to slow down your sending. And that's like, IB does something very similar with its credit system, but that's really what Rocky's doing, is it's applying that ability to slow down a sender when my queue, so not just my whole buffer, but the queue I've allocated starts to fill up.
Yeah, so let's back up here because we started to get into these terms, and I think it's important to get some basics on them first. You're mentioning RDMA and Rocky. RDMA, I believe. What does RDMA stand for?
Remote distributed memory access. So it's, again, the idea that I can read and write to a remote computer's memory. So it's not a TCP socket per se. I'm not enough of a developer to do this very much justice, so I apologize to any listener out there who knows more about this than I do. You're stuck listening to me. Instead of opening a socket and saying like, hey, connect to this IP address and port and send some data, and then they will receive it on that IP address and port, I am going to allocate memory on a remote node the same way I would allocate memory on myself and just pretend like it's local. And so I can say I have 4 gigs of data in memory. That 4 gigs might be across, 12 machines.
Okay. And then, so that's RDMA. And my understanding was that one of the benefits of RDMA is that I can essentially bypass sort of this hit I get from having to go through the CPU.
Yeah, there's some other technologies in there, but that's a big part of it, is that you're not going through the socket layer where connecting via TCP, I'm doing the 3-way handshake, I'm handing it off to a process to another process through the kernel and going on. We not only can go through the kernel, called kernel bypass, but there are other technologies that'll allow the NIC to do the memory read and write. So the CPU doesn't even get involved in the memory writing. So I'm not only bypassing the operating system itself, I'm bypassing the entire compute hardware by having the NIC say, oh, I can write to that memory address for you. I don't even need the CPU to stop doing what it's doing. And now that's even extended to GPU-based RDMA. So the NIC can write to the GPU's memory in that exact same way.
Now, is that what Rocky's job is? And Rocky is RDMA over Converged Ethernet, so ROCE, Rocky.
Yeah, so it's combining that remote read-write capability with the congestion control signaling mechanisms. And so the sender has to know to slow down, right? We do this in TCP by just throwing away packets and then TCP will slow down. We don't do it at all in UDP. And so what Rocky does is it says, hey, we're going to extend your networking stack for RDMA to be able to understand those slow down, speed up messages as part of that congestion control.
And where's that congestion control intelligence living? Is it something that's distributed across NICs, across ASICs, or is there an outside controller doing this?
For Ethernet, it's all within the hardware. So it's the NICs and switches along the path. So each device is responsible for its own buffer congestion or queue congestion. And then if switch 3 of 5 gets congested, it will send back a signal saying, hey, I'm congested, please slow down. And so this is how it manages some parts of Incast and, some burstiness that can happen that doesn't affect the whole network. InfiniBand does this with a controller. So the controller grants access based on those requests, and that's how it prevents the problems from ever happening.
Okay. So Rocky's doing it without a controller.
Exactly. Just like the rest of Ethernet.
Okay. And is Rocky an official industry standard?
think the answer is yes. I don't know if Chris knows for sure. I believe so. If it's not official, it's de facto.
Yeah, good. I'm not sure what standards body owns that. Is that the IETF or not? I'm not sure, but yeah, because well, you had Rocky, and then you'll see Rocky V2, right? So Rocky originally didn't understand or make room for IP addressing, so it was a layer 2 solution, and in Rocky V2, all we're really doing is adding the IP header so we can route it, right? So now we can take that traffic outside the data center, or arguably, clear across the backbone, right? I think might have been Microsoft last year that released a report. 70% of their backbone traffic is RDMA traffic now. And so it's different. We're not talking about clustered GPUs trying to talk across the country, but just the sheer fact that it could be out there already in a routed environment. And it actually could be there, and a network engineer doesn't know it's there. So, you'd have to go out and search for UDP 4791 to find out that it may already be floating around in your network and you just didn't know. Kind of like link local multicast could be floating around sometimes, right? And we don't know that that's there.
And I think that's a really good point to also piggyback on what Drew mentioned is you can have NIC to NIC Rocky. And so the receiver and the sender can send, slow down notifications to each other, and the switch doesn't know because the switch hasn't been configured for it. You do have to go in and configure your switch, configure define your queues, define their queue depth. When do you want to start signaling? And this, again, coming back to like the Ethernet versus IB, to be quite honest, in my experience, configuring those queues is a pain in the. And this is actually part of what leads a lot of people to IB is they're like, well, if I'm this worried about time, I want the plug and play that IB gives me. But again, like there's some of the trade-offs we've already talked about, choice, cost, operations, et cetera. And so, just like anything else, what are you trying to optimize for?
Brings QoS back into the data center, right? A lot of enterprise engineers would say, listen, I've been able to throw bandwidth in my problems for a while now. If we think about my compute layer for an average enterprise engineer is probably 10 gig to 25 gig southbound to compute with 100 gig from leaf to spine. And that oversubscription has been fine for them. I could have 48 ports of 25 gig and just 4 to 6 uplinks of 100 gig maybe. And I have plenty of bandwidth there because I can expect based off of years and years and years of networking that I can oversubscribe the network because my endpoints are unlikely to run at 100% utilization for 100% of the time or extended periods of time. And so now I think it brings QoS back into the data center for these use cases. And this is where maybe there's some, newer terms again for a network engineer, or you have to brush off the cobwebs from old certification exams of priority flow control, right? PFC is a piece of that, or ECN, explicit congestion notification. And to Pete's point, I think, right now there's a lot of manual work that has to go into configuring that. But to me, that's an opportunity for our switching vendors to come up with ways for that to happen dynamically. Read what's going on, see what's happening, and make adjustments as to optimize as you see fit. So I'm really looking forward to. I think we do have to pay close attention now and manually touch that stuff. But with the UEC work and some others, I think the vendors are going to start helping us read more of what's going on in those flows, read deeper into those flows, and then make adjustments on the fly.
So one more question then on this, Rocky. If I'm looking to buy gear, build out gear for Ethernet for AI jobs, and I've decided Rocky V2 is how I want to go, it sounds like I need NICs that support Rocky, and maybe also the switch NOS has to be able to do some configuration to help me on the queue management side.
Absolutely. So you need that across the way, right? So the NICs, the switches, and the NOS. The switch hardware, the switch ASICs, and the NOS. It's pretty pervasive in data center equipment, but it is something you want to make sure you're looking out for and putting on your RFP.
Okay. As silicon gets developed, we've got Broadcom putting out new switch chips, Jericho 3 AI, for example, and there are optimizations for Ethernet baked into the silicon. One such thing with that chipset specifically, a scheduled fabric with credit-based signaling system. Have you guys heard of this, familiar with this, with what Broadcom's putting out in the Jericho 3 AI, and can talk about it at all?
What I do know of is there's actually multiple. If you look at Broadcom, there'll be multiple Jericho 3 ASICs out there, and you'll see the Jericho 3, and then you'll see the Jericho 3-AI, where that Dash AI is not only helping with the scheduled fabric concept, but also trying to minimize what's happening in the pipeline through the ASIC. So I think, we talk about some pieces of silicon are really good at running really fast in a straight line, like a dragster, right? And we think about Tomahawk. If we talk about Broadcom, I think about Tomahawk in that way, where I have really low point latency, but I don't have a lot of features. Like I can't play shoots and ladders game. Like I'm not going to be doing policy-based routing and a bunch of other nonsense, right? Whereas Jericho is more that tank that usually gives me, 101 options of how I can manipulate traffic. But in these use cases, I want to scale that back. So I'd like to have the deep buffers to handle the incast flows. I'd like to have the virtual output queuing, which is built-in system of, a credit-based system inside of either that's one piece of silicon in a fixed form factor or multiple pieces in a chassis. But I want to peel that back to get closer to the Tomahawk type of performance, and that's to remove some of the features out of that Jericho line with the 3 AI.
Yeah, my understanding is it is essentially a credit-based system where you can say, I've got traffic. Are you ready to receive it? And the other end can say, yes, I'm ready to receive. Please send it, or just hold on to it. So, Pete, it sounds like kind of like what IB has from the get-go, but this has been built into the ASIC.
Yeah, and that's that old, is it RSC 1925? Like, everything old is new again. Right. But we've also had something like this for a long time. As a shameless plug, anybody can go out and watch the ASICs for Network Engineers. I talked a little bit about that concept of virtual output queues, VOQs that Chris mentioned, is that in a chassis, your packet comes in the line card, and before it can go to the fabric has to guarantee that the line card it's destined to can receive it. And so it sits not on the fabric anywhere else. It'll actually sit waiting on the ingress card, waiting for its chance, waiting for that credit. That's that virtual output queue. And that exists on, every line card has its own queue, which is why they call it virtual. But again, it's everything old is new again. And so you see these same patterns. So I'm going to take VOQs and it's going to look like the credits in IB, and, we're going to revamp it for AI. So we're going to provide specific priority queues, which just looks like QoS. And, again, the same pattern just repeats and repeats.
Right. So we've talked a little bit about the role of the NIC. Do you anticipate DPUs, data processing units, or smart NICs maybe playing a bigger role in Ethernet fabrics for AI workloads?
Yes, but I think we haven't totally figured that out yet. And what I mean in that sense is that the DPU can do so much stuff. It hasn't totally been figured out what it can do that is worth the extra, if it's a latency hit for extra processing, what thing is worth offloading, some things like that. So I definitely would not rule out the DPU. I think today's DPU, there's not a generalized slam dunk use case, in the sense that if you are doing something with storage or you're doing something with encryption or you have these other specific requirements, the DPU might, dramatically improve things. But I don't think where it is today that it is a guaranteed game changer for every AI workload.
Because, based on what I'm understanding is the name of the game is getting data out of the memory of one DPU into the memory of another DPU as fast as possible. So you want to minimize hops, minimize having to go through some processing stage in the intermediate phase.
And that's exactly right. And part of that's like the NICs that are out there today are so advanced that they can do the direct to GPU data transfer. They can do some of the, checksum or crypto offloading. They can do the RDMA processing. So it's not that the DPU is any worse. It's just a question of what else is it bringing to the table, and does that enhance your workload? And that's what I mean. Like there are absolutely workloads where it makes a difference. It's not universal in that regard. Where like if you go buy a smart NIC, it's got enough features in that toolbox that no matter what you're doing, you will get value from that.
Yeah, and I think a lot of that might be outside of actually the world of AI. Because as Pete mentioned, encryption's now there, right? So MACsec, IPsec, we see that as a feature availability. EVPN, VXLAN to be a VTEP, we see that being built into these. But some of those if it goes back to latency and, do I really want to do MACsec encryption in an AI, GPU backend environment? I probably don't, because I'm adding latency either way. If I'm going through another chip, even if it's hardware crypto, I'm still adding latency, right? Even from an EVPN VXLAN standpoint, I'm proposing to add an NCAP and a DCAP process to it. But I think it was Del Oro, like a couple of years ago, 2022 might have been. I think they predicted SmartNICs would likely have about 36% of the industry by 2026. And then I just saw the reason this comes to mind, a week or two ago, I saw an update from Del Oro, and I think they were calling for, something like, I don't know, $16 billion worth of, industry value to DPUs by like 2028. So I think the SmartNICs will show up. I just don't know that they would all be specific to these AI workloads.
If I'm a network engineer designing a data center for these sort of workloads, what are the design considerations that I would need to keep in mind that maybe I wouldn't because these are so different from what I've typically been building for?
Money.
Power, cooling. Yeah. Before you even get to power and cooling, I'll tell you one thing that jumps out at the network engineers I talk to about these is that oversubscription versus what I call over provisioning. Where, from leaf to spine, I mentioned earlier, if I've got 1025 southbound, I've got a couple of uplinks of 100 gig and I'm fine. In these environments, for every bit that you show southbound to compute, you need a matching bit northbound to the spine.
1-to-1, no oversubscription.
No oversubscription. And in some cases, they want it to be better than that, right? Where they want extra.
Because you could still have contention to deal with. Yeah.
Contention. And we go back to the MTBF thing, right? We're going to have a bunch of link failures. We know we're going to have link failures in these environments where there's a lot of GPUs involved. And so, yeah, you'll see the optic element to these designs, shoots up exponentially, where we're going to match. Like if you just picture, hey, if I've got a 64 port switch, like a 2RU switch as a top of rack, I could take the 32 ports and head southbound, and I'm going to take the other half of that switch, the other 32 ports, and go northbound to my spines. So it really changes how you look at the capacity of a switch for what you're being able to allocate to that southbound compute.
And to make things even worse, I think that historically we see a server in a rack and we think 1 or 2 ports of connectivity, probably 2, NLAG, whatever. A lot of these are doing NIC per GPU. So each GPU gets its own NIC. So you're seeing servers with 8 NICs in them. And then that ends up meaning I need 8 NICs per server. I need 1-to-1 oversubscription, so I can only use half the ports on my switch. So I've seen some designs that are 4 or 6 TORs in a rack, just because that's what you need to do to keep that oversubscription and that port density in line. And then once you get to the scale out and you start looking at the spines in that network, you're doing 100 gig to the server. Now you need 400, 800 gig spines. And that you get to this point where if you can only grow the cluster so large before you say, look, if you're going to go between these clusters, you could have problems because we have to go through something that's oversubscribed. We just physically cannot give you more bandwidth between this many nodes. And again, referencing that meta paper earlier, they talk about how they basically built the leaf and the spine out of 1RU boxes, and then their super spine are deep buffer bay chassis because of exactly that problem. They're like, this is where we're going to have more contention. This is where we have more oversubscription. Anything that's going to go between clusters, we have to worry about. And then that even comes back to like getting your network topology to start working with your AI people to know where they can and should deploy these jobs from a locality perspective. And again, talking about cooling, a couple of these 1RU switches, can roast hot dogs. You put 4 of them in a rack on top of a whole bunch of GPU nodes, you're really cranking up the heat. And so we're seeing a big trend in what's called like closed loop liquid cooling. So liquid cooling is immersion, where like it's the things like in a fish tank full of oil and it looks crazy. That's the other type of liquid cooling. In this case, what it is it's a metal plate, looks like a heat sink. It's got 2 hoses plugged into it. and those hoses carry the coolant through to the metal plate. It passes through the metal plate, collects the heat, and then goes out the other side. And then you have, something that's either a couple of RU in the rack, or, it's a full cabinet size thing at the end of the row that is a big radiator that is cooling that warm coolant back down to pass back through. And we're seeing that on the compute, on the GPU, and even in some places on the network components now.
It's just, again, going back to the money and all of the demands on the environment for this stuff. I hope the payoff is there at some point, because ChatGPT is cool, but in similar things. But I'm not seeing it being the world changing thing yet. So I don't know. I
still have a small child, so I'm just hoping computer vision gets to the point that it'll fold laundry. Whatever it took to get there will be totally worth it.
So
these systems show up and the entire organization is impacted, right? It's not just a network team. It's not just a platform or compute team. Your storage team's impacted because they're probably going to look for some sort of optimized storage solution in this case. And it's not necessarily the usual suspects in the storage realm. The power, we talk about power all the time because Pete mentioned, you're going to have either 4 or more likely 8 GPUs in a host. And if each of those GPUs are in the range of 750 watts to 1,000 watts each, you go from what is the average enterprise rack at, maybe I'm used to 6 to 10 kilowatts of power to I'm way north of 20, or in the case of some of Pete's projects with that NVL 72, I think it's 120 to 100, maybe 200 kilowatts of power. So then you think of the whole data center and you say, okay, well, the average enterprise data center is probably 10 megawatts. And then you look at Alibaba talking about, hey, our 15,000 node clusters required about 150 megawatts of power. Or if you look at Tesla or XAI, any of those projects that are going on, you see a lot of talk of not only 100 megawatts, but 150 to 200 megawatts, which leads to the jokes of us finding things like AWS having bought land adjacent to a nuclear power plant in Pennsylvania, right?
Not jokes. Yeah,
not jokes.
These things are happening globally. Where the problem data center providers are having has to do as much with power and cooling, access to water in some cases, to be able to just keep the facility online. It's not, and they're getting turned away in different locales. It's not even possible. Then the numbers, you're talking megawatts. If you're listening and you've never worked in a data center environment where you had some sense of how much power is being consumed. I used to work in a data center where we cleared payments for some of the largest companies in North America, including Amazon and Verizon Wireless and so on back in the day. We ran the whole data center. Our backup generators were 4.5 megawatts in aggregate. There were 3 1.5 megawatt generators sitting on platforms outside that could easily run the whole thing in an emergency if necessary. And typically we were drawing way less power than that. Now we're talking about these large data centers doing AI modeling that are 100 times that kind of power consumption. We were talking to somebody, I don't remember who it was, but they were talking about 700K in a rack, I think, in a 42U rack. There's 700 kilowatts in a single rack. It blew my mind. I forget what all was in that rack, but the power requirements are astronomical to pull this stuff off.
Those are similar to some of the systems I'm working on. So it's 16 compute sleds. Each compute sled has 2 GPUs. Sometimes there might be doubled up compute sleds. So up to 72 GPUs in a rack plus 32 or 64 CPUs alongside. And then the non-Ethernet networking that is baked in, it's not IB either. It's a custom, chip-to-chip fabric that's burning a bunch of power for those ASICs. And then you get to slap your Ethernet switches in there.
Yes, it's crazy what things have gotten to now. Again, hope it's worth it. Telemetry, observability, management. How am I tracking this whole thing? It ain't SNMP polling every 5 minutes, I'm sure.
I think this is one of the challenges today. Is it's management monitoring has never been a strong suit of networking, and now all of a sudden it got real important, real fast. And so I think that's really challenging. And then I think the other challenge is coming back to like everybody in the stack matters, right? If the OS is adding a couple of nanoseconds of latency, the network's going to get blamed for that. So how do you start to manage your end-to-end latency accurately? How do you monitor, your drops and your congestion and whatever else you have going on in the fabric? And I think those are everything now suddenly matters. All that stuff that you never cared about before, besides like smoke ping, now you care about all of it.
Yeah. Well, thank goodness Open Config and streaming telemetry has been around for, I think we're probably around a decade or close to a decade now. We certainly need to rely on that. Your point about SNMP is spot on. There's just no way we're going to do this with SNMP. And an understanding that it's not just, from a network engineer's perspective, looking at the leafs, the spines, and the interconnects between them, but you want visibility into the systems, right? So whether if it's an NVIDIA box and it's NVLink, right? There's a network of connectivity, GPU to GPU, in addition to the PCIe that's in there. NVIDIA has that, AMD has, I think it's called Xfinity. There's a network in there that you want to be aware of, because that could be where a bottleneck is happening, right? I mean, we are talking about a lot of components. There could be failures at any point here. So you're going to want visibility not only for your network gear, but inside those host systems as well, which some of that communication that, you try to optimize some of that where it's even cabled differently. We hear a lot now in 2024 about rail optimized designs, where, if you think about the GPUs in the system, if you were to number those 8, like 0 through 7, every GPU 0 in every single host would be cabled to leaf 0, for instance. And then GPU 1 in every system would be cabled to leaf 1, so that then the system, as it understands and discovers what the network connectivity is, it can optimize its form of communication and then figure out when it's best to use something internal, like an NVLink path, versus writing out to a top of rack or even to a spine.
So switch vendors are often using the same merchant silicon, so the same ASICs, the same NICs. What are switch vendors doing to differentiate, especially if, the optimizations are happening at the ASIC level? What does a switch vendor bring to the table?
At least what I've witnessed, what I've seen in POCs or head-to-head battles, if you will, it's the software matters. Whether you take every bit of software provided by, if you buy merchant silicon from somebody and you put it inside of your sheet metal, how much of that software do you take with that merchant silicon and how much do you rewrite yourself? So I think a lot of it is, for each networking manufacturer, what they do with their software, and then features, right, in addition to that. So it's not just, can my software write faster or detect faster, respond faster? But also what features do I have? Things that, enhancements for things like load balancing is an example. I think it's probably one of the biggest ones. Or, Pete mentioned RFPs. And I think a lot of this is paying attention to what should I put in that RFP? What should I be looking for from a feature standpoint inside of these networking devices? And the load balancing, the visibility, the latency visibility inside of a box to be able to tell if it's a fabric module that's the problem or any one piece of silicon that's the problem on ingress or egress. And what other features, what nerd knobs do I have, right? As we tweak it, as we've gone through POCs, there's been times where, PFC is the perfect solution for a specific workload. And then at other times we found that in this case, I really need ECN and PFC to be working in conjunction for this type of workload. And it can vary by workload. It can vary by project, not just by customer. So there's a litany of things I would pay attention to if I were to be trying to prepare to build one of these things as far as what I would put on that RFP. One of the ones another one that comes up is PTP. Right. A lot of times we've been living off of NTP forever. I joke, you just Google the free NIST servers out in Colorado or whatever, and you point at that. That isn't sufficient here in these environments. We want PTP. And if we want PTP, then we're going to need hardware clocks inside of these systems. So it's another piece that could be a differentiator is, do I have hardware PTP clocks in here?
That's interesting. Yeah.
And not so much about the vendors, but I think in general, a big takeaway, in my opinion, is like this is a big architectural thing. The closest I can think of is like bringing voice and video into the network for the very first time. You can't just take whatever network you had back in 10 base T days or whatever and slap in some telephones and just hope for the best. Like, you were putting a totally different demand and workload and set of requirements in that environment, unlike anything that's been there before. And it's a lot. And if you think that you can just slap, replace your 10 gigs with 100 gigs and your 100 gigs with 400 gigs, I think you're going to be in for a bad time.
But that is a good example of bringing the flexibility of Ethernet, or what the forced flexibility maybe of Ethernet. Hey, we took voice and we put it in there. If I look at some of the projects today in the media and entertainment environment, right, and getting away from some of their legacy analog stuff, I see media and entertainment engineers going through that struggle, just like a hardcore voice person did when you told them they're going to move their stuff over to IP. So, this could just be another thing, right, that gets rolled up into Ethernet, as those technologies did as well.
But we've been talking in the context of these really huge AI clusters. I mean, the average person sitting here, they're not going to be working on that network because there's only so many of them in the world that exist. Is it likely we're going to see smaller AI clusters that have similar problems, but they're just scaled down from these massive installations we've been talking about?
My possibly loaded opinion is smaller. It doesn't make sense to build a smaller cluster unless you have real data sovereignty and privacy concerns, because it's so hard to get the gear. It's so hard to build these and so hard to get them right that, one rack can hold, I don't know, whatever, 32, 64 GPUs. Like, that's a lot of power. And now if you're going beyond that, now you're all of a sudden into this architectural space. And so if you can do all of your work in like 16 GPUs, maybe just go to the cloud. You can get availability. You don't have to worry about it. I mean, this is, again, like the same argument we've been having in infrastructure space for years of like build versus buy.
Yeah.
And, a GPU node from AWS is really expensive. You know what else is really expensive? Like multiple megawatts of power.
Yeah.
I mean, the whole thing around AI networking, when we're talking about GPUs, is we're talking about two nodes with a GPU in each talking to each other. And then everything is just more of that. How big is that cluster that those GPUs think they can talk to? So, I mean, there's nothing that stops you from getting, a pair of Raspberry Pis with GPUs on them, or, whatever that equivalent is, or getting a couple of like low-end servers and buying a pair of NICs and low-end GPUs to build that example and start to understand some of the RDMA, RoCE, Ethernet components. But like I said, I think it's a big decision for an organization to decide to start to build one of these things. And I think you can get a lot of juice out of just the cloud before you actually have to start building it internally.
Chris, any thoughts on that? Because I do think it is a decision organizations are going to have to think about to DIY it, or go to like a specialist provider, or go to the cloud.
Yeah, I think a lot of us are of the opinion that, this work is being done in the CSP space, and you're going to buy those services for a while. But then at some point, those bills do come in. You do look at the ROI, and then you do try to determine, would it be better to bring this in-house at this point? Did it work for us? I tend to think we are going to see these in the average enterprise. No, it's not going to be 10,000 GPUs in a cluster. But I think to see several hundred to 1,000 would be doable from a power, being able to power that and being able to manage that. I could see that happening. Or that GPUs just become more of the buying criteria. Maybe we move away a little bit from caring about what a CPU is, right? I look at it similar to a switch. Like, I don't have too many customers that ask me what CPU is inside the switch, but they certainly ask about the silicon, the ASIC, right? And the heavy lifting. And I just wonder if compute wouldn't trend that way. And maybe that's what we'll see, is that we're going to be networking for GPUs because those are the brains of the box. And that CPU is relegated maybe to more of the control plane type of stuff, like similar to what we see in the network environment. So I think these are going to be here. I think they're going to show up. It's early. We're certainly in the we're beyond the innovators. I think we're in the back half of the early adopters. And, we're well ahead of the early majority. But we see global financials with these projects, right? We see folks working on fraud detection. We see folks wanting to get better at executing their trades. So the global fives are there, and they're usually the ones to follow along quickly after CSPs. And I think it'll trickle into everybody else. But ultimately, in the end, to me, it's the fun of what's going to happen to what I do day in and day out and what additional features am I going to get. I think that's the bigger part of this is to watch what happens in this space, and as it unfolds, knowing that the average network engineer is going to be bettered by the features and the enhancements to come. Even maybe it's just visibility simply that gets better for you, 18 to 24 months down the line after the CSPs vet it.
Chris, I like the way you sort of frame this as for network engineers to think about moving away from, it's less about AI and it's more about moving away from networking for CPUs to networking for GPUs as a way to kind of hold it in your head, because AI is a loaded term. Speaking of which, closing question, and you guys can answer this or not, depending on how comfortable you are. Are we in an AI bubble? What's your feeling?
As an NVIDIA employee, absolutely not. I think my real answer is, what is AI? It's this phenomenal pattern recognition machine, and it can detect the most minute and minuscule patterns. And I think that we look at GPT or, the Gen AI stuff, and it's like really cool and novel and also weird and creepy. And that's not going to, I think keeps it in the conversation today, but that's not going to be the game changer that, we thought it might have been a year ago. But I think you look at things like medical imaging, fraud detection, anywhere that you can start to pick out these, you're looking for a special type of needle in a whole pile of needles kind of problem. Like AI is really good at that. And that, I think those kinds of use cases we're going to find over and over and over and over again, and that will make it pervasive, as opposed to my barometer has always been once computer vision gets enough to fold towels, because it's actually a really hard computing problem, right? A computer cannot look at a pile of laundry and regularly, predictably pick out a towel and fold it. That should be easy, but it's really hard. And so I think it's less about those things that are easy and obvious for us, and it's going to be more about a million small to medium sized things that add up to a revolution.
Yeah, I would second that, Pete. I don't think we're in a bubble. I think maybe it's just that these tools, these applications, the problems that are being solved they aren't necessarily consumer facing, right? They're internal problems in a children's hospital research group, as an example, right? In gene or cell therapy. I just think a lot of it's not something maybe I get to interface with every day, but pervasively it's out there. And there's a couple, schools of thought as you try to figure out, how much or what percentage of Luddite you might have in you. But, whether you're reading Ray Kurzweil's, The Singularity is Nearer, right? A popular book having come out this year, or another one, there's a popular paper that made its way around Silicon Valley, I think maybe a couple months ago. It was called Situational Awareness by Leopold, and I'm going to screw this up, and I'm so sorry, Leopold, but Leopold Aschenbrenner, I think is his last name. But if you just search on situational awareness, and he explains, hey, this is what we've seen, right? This is a progress we've made. And if we just follow that, if we treat this as a math problem and play this out, he predicts, in his opinion, where we'll be over the next few years. But I don't think we're in a lull. I just think we're as an average everyday consumer, we're just not seeing the sexy tooling past GPT-4o.
All right. Well, we've kept you guys on here for quite a long time, so really appreciate your time. Are you online anywhere if folks want to get in touch or just look you up? Do you have blogs, LinkedIn, whatever?
You can find me on LinkedIn, and I'm still on a platform formerly known as Twitter, Pete CCTE, where I mainly complain about things and make dad jokes.
Excellent.
Yeah, I'm also on LinkedIn and Twitter at CCIE 14430. And there you'll usually see me talking about the networking user group stuff, which is where I really get to interact with a lot of folks, is with the NUGs around the country.
Excellent. We'll have those LinkedIn links and Twitter links in the show notes that accompany this podcast. Chris and Pete, thank you for this conversation. I hope it spurred folks to do some more digging. And to that end, we have lots of links in the show notes if you want some good resources to get yourself started. Speaking of resources, you can find this and many more fine free technical podcasts and our community blog. It's all at packetpushers.net. If you have comments, questions, or clarifications, you can hit us up at packetpushers.net/FU. The FU is for follow-up. You can find us on LinkedIn, hear us on Spotify. And if you would, leave us a rating on Apple Podcasts. Last but not least, remember that too much networking would never be enough.